Okay, perfect. Thank you everyone for turning up to this talk. It's a part two of the talk. I'll share these slides after the talk. The part one was presented here last year. It was about a new line process that we were developing called binomial line Cox process. I'll do a brief recap of this talk so that we come back on the same page and then continue it to discuss urban streets and this new parameter called successive successful detection in automotive radars. So basically, it's divided into three parts. The first part is the recap of part one, some real data-based parameter selection. The second part is modeling automotive radar networks using this new line processes, this framework of radar tracking, and the third part is about QoS-aware optimal frame design in radar tracking and some numerical results. Okay, so recap of part one. So in part one, we were motivated by this fact that urban streets appear with different street densities as you move from the city center to the outskirts of the street. So here I have with me a map of Paris, zone 1, I think only, where the streets appear a bit more regular or homogeneous in this sense that wherever you go inside the city center, you have more similar type of intensity of streets around you. Whereas if you look at the larger Paris region, you would see that if you move away from the city center and towards the outskirts, you would have rarer and rarer streets. So traditional line processes, which are more homogeneous in nature, fail to take into account this aspect from the perspective of a single city. So if I want to address or study the performance of any communication network or any type of framework that transcends or starts to experience these different parts of the city, a homogeneous model is not good enough. So we would want to have a model which emulates this kind of behavior from the perspective of a city. So in order to do this, we introduced something called binomial line Cox processes. So unlike the Poisson line process, a binomial line process is generated by a fixed number of lines, which are generated inside a generating set, which is a circle which we will call the radius of the city. So for example, for Paris, it will be zone 1. So lines are generated inside this. No lines are generated outside that. And we'll say that it emulates this decreasing intensity of streets in a better way than what homogeneous line processes do. The location of these generating points are uniformly distributed in that generating circle. The generating circle would be somewhere like this, where the lines are generated, and uniform angles. On each line, we can model locations of lampposts, location of vehicles, location of base stations or cars, whatever, by using independent Poisson point processes on each lines. The structure that we have as a union of all such points were called binomial line Cox process, similar to Poisson line Cox process. So this is one kind of realization. So this is a Poisson point process with an underlying intensity, which is matched to roughly the intensity of this binomial line Cox process, where we have fixed number of lines in a fixed area, which is NB by 2 pi r. So we have this kind of structures. And our claim is that if you want to study only the city center or more a homogeneous kind of a structure, you are free to use this Poisson line Cox process. But if you want to model the experience, let's say of a vehicle traveling from the city and going outside and how its experience of the network changes, maybe these kind of models are a bit better. So what did we derive until now? We derived the distance distribution to the nearest line in a binomial line process, depending on where you are located. So if you are in city center, your nearest street is probably nearer to you as compared to if you are in the outskirts. We also derived the line length density, which is the kilometers of line per square kilometer of area as you move away. So all of these were in the first part of the talk. The intersection density, this is also important because number of accidents is related to the number of intersections, or maybe opportunistic deployment of base stations is also related to the number of intersections. And then we characterize the probability generating functional, transmission success probability, so on and so forth. Okay, And also we did the meta distribution analysis, which was presented last time. Now, once we have this model, we would want to see how good or bad this actually answers our question, which we wanted to do, which is better emulate the streets of a city, right? So for that, we have this OpenStreetMap from where we can put a Python library, OSMNX, I mean, whichever anyone can use. You can basically download the map and it gives you street density, it gives you street lengths. If you fix the area, you give the latitudes and longitudes where you would want to analyze, and it returns back this kind of data. So basically, it's used for data retrieval, graph construction, geospatial analysis, so on and so forth. So using this, we did for 14 or 16 different cities. I've presented a couple of them. The same observations hold actually. So even if you look at Paris and look at the outskirts of Paris, there is this fewer rarer streets going up. Even in New Delhi, the central New Delhi is more congested, and then when you go out, it's more rarer and rarer, and this is what we would want to emulate. So we tried to do curve fitting. So we found out we tried to find out parameters for the Poisson line process and the binomial line process, which minimizes the Kolmogorov distance between the actual data, street data, which is length of streets, as distance increases from the center of the city. The units are in meters here. So for Poisson line processes, which was restricted, which is more a single parameter model, which is the intensity of streets, there was less flexibility of fitting this data. So you would not able to match accurately what the real data actually did. But now PLP, by virtue of it being two parameters, you can better fit, and actually it matches quite nicely with the intensity of the actual streets that you observe. So this is A is for Paris and B is for New Delhi. There are more length of streets. I mean, you can just observe that there are more length of streets as it goes um, from the city center to the outskirts. You will also see soon that Paris, with a fewer density of streets, a fewer length of streets, also has a larger density of vehicles, which will together result in some huge difference in observation of how a radar would perform in a situation, the same situation in New Delhi versus the same situation in Paris. Okay, so for the Cox model, we have emulated the streets, but now we need an intensity of base stations on the streets.
Okay, yes. Just a question. So you try to the previous slide, you try to fix to adjust some the parameters of that correspond to the length of the streets, but is it the right parameter to adjust? Because you may have also in terms of network the degree of the graphs and other parameters. What push you to what are the arguments for you to focus on this parameter?
Right. So you're right. You can actually match the intersection density as well as you move out, or the degree of the streets, as you rightly said. This was more related to the average number of points that you would observe. So since it's a Cox process, it's the density of the points on the length of streets. So larger the length of street, more on an average points you would observe, like base stations or cars or something like this. So that's why we first match the length of the streets for this study. The next thing that we need are the density of the points on the street, which is influenced by city characteristic. Let's say if you have a lot of public transport in a city, you would have fewer cars, ideally, and time of day, peak hours versus off-peak hours. What we observed is that hourly traffic density follows a bimodal profile. It's not surprising. It's high during the office hours of the day and when people are returning back from office to their homes with morning and evening peaks. So what we did was find out a peak vehicular traffic intensity, which is a peak traffic occupancy multiplied by total number of non-commercial vehicles. This is, we needed to go through a lot of government documents to find this for every city, divided by total street length, basically. And then we have a app, TomTom, which gives us congestion time. So if you give your source and destination, it tells us how much time you would need to go from here to there, and this time varies as time of day. So it is again high during the peak hours and low during night and so on and so forth. We assume that the congestion time is directly proportional to the vehicle density at the streets. This is an assumption. So more the density, more time you would need to reach your destination. Using that, we multiply this congestion at a time I divided by the maximum congestion time that you observe, multiplied by the intensity, total intensity of vehicles at its max. That will give you the intensity of the vehicles at a time of the day. So this will bring back this when we do our numerical analysis. Okay, so this is some kind of approximations that we reached with this philosophy. So we see that the intensity of the vehicles as hour of day goes, the unit is per meter. So this is, yeah.
Is there a relation between traffic flow and the street density?
Yes, and this is something which we have not studied. There is also correlation. So many crowded streets are, if they flow onto a single street, that street will of course also be crowded and so on and so forth. This was not modeled yet. Okay, so Paris has a large number of vehicles per unit meter. Not very surprising, but okay. These are four things that we will be used to. We'll bring back these values later on when we discuss the numerical results. Just to say that okay, these models are developed theoretically, but we have some kind of real values to test our numerical results. Okay, so the second part is where this talk begins is how to use these line networks or line models to model automotive radar networks. So if you look at this scenario here, and we assume that ego radar, which we will call our test radar or test point, is located at some part of the city, and it's looking towards and it's going in its own street, which is modeled by the y-axis, and it has a radar sector which is governed by the beam width and the maximum radar range. So this green part is the radar sector formed by this particular radar. It experiences some other vehicles in its radar sector, which are potential targets, but are potential interferers as well. So vehicles, we will assume that vehicles are mounted as radars on the ith street, and individually on street, it's a Poisson point process with uniform intensity. By the way, this intensity can also be modeled to vary as a function of the distance. So as you go farther and farther from the city center, you will have fewer and fewer cars and so on and so forth. But for the moment, this is uniform.
I do not understand the angle for this sector. Because we are considering streets, I would have expected to have a view only on the street, not in streets that are outside.
Right. So basically, when we are interested in highway kind of a scenario, I'm more interested in tracking my next vehicle which is in front of me or the targets that can come in front of me. But when I am in a dense urban scenario, I would also want to know if there are oncoming targets from other streets which are intersections. I would want
visible except at the edge.
Right.
They will not be visible.
Right. So when you reach this intersection, right, you would want to increase your beam width a bit. Otherwise, you would miss possibly the targets which are kind of coming in.
You have a radar at each vehicle. So will there not be more probability of ghost targets? Or
I'll come to this point. This is an important point. We'll discuss this a bit. Okay. Okay, so our analysis focuses on automotive radar mounted on the typical or the test ego radar, which is moving around in the city. Okay, the complete distribution of the vehicles we model as this binomial line Cox process. The vehicles from the opposite side of the road on the same street as your vehicle is. So it's a model which you can modify. So you can remove the other streets if you only want to study your own street, which is a better model for the highway kind of a scenario, right? So that is an L0 which is put on top of the binomial line model that already exists. Okay, so traditional radar metrics are probability of detection and probability of false alarm. So generally, it's whether your signal plus noise is larger than a given threshold, which is the probability that you are detecting. or whether your noise is greater than that same threshold, which means that there is not a target present, but you are still detecting it. So these are your traditional metrics of studying radar performance. You draw your radar operating characteristics, which is probability of misdetection versus probability of false alarm, and that kind of characterizes your how the radar performs. However, some experimental demonstration said that the signals from automotive radars, which are oncoming to your radar receiver, will create interference like noise like interference additional phenomenon rather than ghost targets. So hence it's important to model it like this, the interference like this, like you would do in a communication system. So in your communication, you model your SINR, and this automotive radar interference has the same kind of behavior rather than creating ghost targets as clutters do, right? So if this is our model, we are interested in whether this SINR is greater than certain threshold, and we will call it the probability of detection. I'll motivate this parameter, this metric a little bit in the next slide. But here, what I'll explain this a bit more. So in this SINR equation, the signal consists of the power transmitted, the distance to the target, which is capital R. It's a two-way path loss because it goes, bounces off the target and comes back. So it's R to the power minus 2 alpha, unlike the single way path loss in a communication system. Sigma C is the fluctuating radar cross section. So if you see a motorbike versus a vehicle, its cross section is fluctuating. Sigma C is a random variable which models the fluctuating radar cross section. It also depends on the orientation of the target as well. On the other hand, the interfering signals are single way path loss, so it's to the power minus alpha, multiplied by a fading parameter similar to how you would perceive your communication signals. And then you have this noise. Another way to interpret this CCDF of SINR is like this. So suppose I draw the distribution of signal plus interference and noise, which is the blue one. Statistically, it's larger than the only interference plus noise. So my probability of detection or probability of false alarm is dictated by how I choose my detection threshold. So if I choose my detection threshold, let's say where these two curves, two densities cross, then the shaded region in red is the probability of false alarm. The probability that my signal is that my noise and interference is greater than that threshold, although no signal was present. Now the separation between these two plots, the SIN and the I plus N, more well separated they are, more will be the SINR. I mean, more the SINR, more well separated they will be. Right. Now this gives me more agility or more possibility to select this threshold in a good way that minimizes both the probability of detection as well as the probability of false alarm. So you want to maximize detection. That means you would want to choose the threshold in such a way that whenever there is a signal, you would want to detect it. You would also minimize the false alarms, right? If they're well separated, if they're completely separated, then of course you have good flexibility. So this is another motivation why studying this metric, which is not a typical metric in radar studies, is also useful in studying radar systems. So for careful modeling, it's like this. So suppose you have an ego radar. I have two instances of the ego radar presented here. Now, who will create this interference? Now we have established that modeling interference is important. So as to develop probability of detection. So which vehicles will create interference? Those vehicles will create interference which simultaneously are present in the radar sector of the ego radar, and also the ego radar is present in their radar sector, because otherwise the beams will not merge. Right? So vehicles can have forward-looking and backward-looking radars, but they might not interfere because they are not in each other's radar sector. So in this example, the violet vehicle does not interfere because although it is present in the radar sector of the green one, in its radar sector, the ego vehicle is not present, and so on and so forth. So this needs a bit more careful modeling and calculations, because now you have a non-isotropic structure, which is the radar sector, moving through the city, which is a bit more isotropic. So you have to calculate possibilities of where these intersections can occur, where these interfering radars can lie, and it will actually also reveal the question that when do taking into account the other streets become important, and when only my street is the major contributor of my interference.
Gourab,
So
may I ask
basically, if you
may I
have
ask
an
a question?
interfering street,
May I ask a question?
we can have a different kind of propagation or penetration loss for the buildings that may be present in between the streets. For this study, we have ignored it for the moment. But for a given intersecting street, which is at a distance of di from my ego radar, there exist limits within which a vehicle, if it is present, then it will create an interference to my ego radar. Because if it is present before that limit, then the ego radar falls outside its beam, like this blue one. It falls outside the blue one's beam. But if it's present beyond the limit, then it is present outside the radar sector of my ego radar. So there is a limit for each intersecting street, where if a vehicle is present, it will actually contribute to the interference, and it also depends on how far the intersection is. Closer you are to the intersection, more will be the area in which you need to take into account the intersection as well. If the intersection is far, it's correct that you don't need to take into account it as well. Okay, so if I find out these limits, then I can find out the direct distance, I mean using trigonometry, to find out what would be my quality of the interference signal. So this is a complicated procedure because there are many different possibilities that can arise. If you have a radar sector, an intersecting street can cross the top of the radar sector and one side of it, and different cases. And that's why you thank the graduate students who do this painstakingly for each and every different case. So we have found out what would be the length of the intersecting streets for each case, and accordingly what would be the contribution of the interference on each case. So two things matter: how far your intersection is. It matters what is the angle of intersection, because if it's a 90-degree intersection, maybe interference will not be too much of an issue. But if it's oncoming to you, it's important because not only the interference, but also you might be, I mean, they are potential collision instances because they are oncoming traffic. Okay, so on basis of this, we developed we plotted the detection probability, which is the probability that the SINR of the radar signal is greater than a certain threshold for different cities. And this is where so here we ignore the penetration losses due to buildings, but they can be included as well, but they will be included in all different cities as well. We have a stark difference between cities. So here we have 25% or 0.25 detection probability, whereas cities which have more streets like that one, just because you have fewer vehicles, you have less amount of interference and less detection. Yes.
So in this radar, you transmit a pulse for short duration, or is it a continuous?
Yeah, it's a train of pulses. So we are until now, we are only interested in one shot detection, one pulse, whether I'm able to detect or not. But in the second part of the final part of the talk, I'll move to consecutive detection with a train of pulses. Okay. It varies from the perspective of where you are located as well. This is the motivation to study binomial line processes. The same radar parameters, which means that if you keep your radar beam the same, transmit power the same, and your interfering vehicle intensities remain the same, the experience that you will have in the city center is very different than the experience that you will have in the suburbs, because there are no too much intersecting streets and so on. This is the kind of insight which is missed by models like PLP because it was homogeneous everywhere. Now you can have studies based on where you are located. So for example, 4.5 kilometers away, you have better detection probability just because there are no intersecting streets and so on. Okay. After the radar detection, we develop a new concept of a metric called radar tracking. It will also help us develop a new stochastic geometry metric, which is successful successive detection. So I'll explain what this is. Let So we have established that, okay, studying interference is important, experimentally demonstrated. How we can model interference based on this line processes and the Cox processes on top of it, and how individual streets contribute to this interference. So if interference is so well modeled, so to say, we would want to see how we can alleviate it. So let's say that I have a MAC protocol for radars, where the time frame is divided into blocks of T slots each, right? So let's say you have a total time of radar tracking or detection, and it's separated into different blocks of each block having capital T slots. Now what happens is that in each block, each vehicle of this point process, which is the location of the vehicles, operates with a probability delta. So it's not slot wise aloha, it's block wise aloha. So you compete, you get access in the block. If you get access in the block, you transmit in all the slots of that block, and then you wait for the next time you get access. So within the block, an active vehicle attempts to detect the target in all the capital T slots. If you didn't get access in that block, you have to wait for the next block to get access. Similar to before, we say it's a successful detection if in a slot your SINR is greater than the threshold gamma, right? Which is classical. But let's say that capital L denotes it's a random variable, which tells me it's the run length of detection successes in a block, which means how many consecutive successes you have had. You can think about it as tossing a coin capital T times, and L is the number of successive heads that I have had. Right. Now I will say that I have a successful target tracking if I am able to detect the target in a in successive new slots. So if L is greater than equal to nu for some nu which is less than equal to T, then I will say that in that block, my target is successfully tracked, not only detected, but successfully tracked. Now, this is a bit more challenging to derive because there is correlation among the tracking events. So if you think about a block of capital T slots, if your requirement is T slots of detection to call it successful tracking, there is only one possibility, all should be successful. But if you have T minus 1 as your requirement of tracking, then there is two possibilities, from 1 to T minus 1 or 2 to T. But if you have told that 1 to T minus 1 was successful, there is more likely that the 2 to T was successful. Right? So there is this correlation which has to be taken into account. Okay. Like before, we derive first the conditional success probability. So in order to derive the detection probability. So this is conditional detection probability that my SINR is greater than a threshold for a given realization of the point process. Now, this is quite common expression in stochastic geometry. One part accounts for the noise, the second part accounts for the interference. There is only one difference, is that since there is aloha happening, but it's not every slot, so the transmission activity of each interferer is not averaged inside the aloha expression. So it's not one, so P times the interference occurs and 1 minus P times the interference does not occur, but rather the impact of this aloha is directly in the point process itself. So it's a thinned version of the point process. So P times lambda is active in that block, and 1 minus P times lambda is inactive in that block. If it was per slot, then the point process would be all the points, but with probability P each interfere and 1 minus P each do not interfere. This is a slight minor difference in these two frameworks. Now, once we have this conditional success probability or conditional detection probability, we can derive its moments. Is the Lth moment of the detection probability. So the conditional detection probability is a random variable because it's conditioned on the point process. So we have the moments of this random variable as the conditional detection probability. We'll use it to later characterize the tracking event. This expression, again, it's a bit complicated because two lines, but we can follow it. The first expression corresponds to the noise. It's the typical probability generating functional for the Poisson point process. It's not the noise. It's the line in which you are present. So it's 0 to infinity PGFL of the Poisson point process. So if you want to take into account only your line and forget about the other intersecting points, you just ignore the other parts. The other parts corresponding to the intersecting lines, which is a probability generating functional of a Poisson point process for intersections which also follow a Poisson point process on your line. So intersecting points are Poisson arrival process in your own line. And on each line, there is a corresponding AI and BI through which you would want to integrate to find out the interfering distances. Now, this is the part which we discovered. So we tried to do this for some time. It was becoming a bit more complicated, but we kind of re-derived an expression which existed for more than 200 years, I think. So it's an exact result of what is the probability that the successive number of heads exceeds nu in a sequence of t tosses, right? So this is your tracking event. So it's the probability that the successive consecutive successes L is greater than nu for a given realization of the point process. Now with this expression, the probability of detection appears in some places. We might be interested in the, okay, before going there, we have a couple of small results. The expected number of successful tracking events. So if you have capital T number of slots in a block, as I said that if your requirement is nu equal to T, you have only one possible tracking event. Either you are successful or you are unsuccessful. But if you have lower number of tracking requirement, then you have more possibilities of having successful track. So even if you fail in some slots, it might be possible to still track your target within that block if sufficient number of slots are remaining. So the expected number of successful tracking events in a block is given by the moments of this conditional block detection probability. If T equal to infinite, which means there is no MAC protocol, you are always transmitting, then the sum of all the moments gives you the expected tracking length. So expected number of successive successes that you have.
Then, here you have nu and T as parameters.
Yes.
There is no trade-off in terms of latency or something.
There is.
T.
Yeah.
Okay.
It's the next part. Yeah.
And on you, I was rather expecting that you, as the number of samples increases, your accuracy or your confidence in detecting a vehicle is higher and higher. And then we can decide when we reach 99% or something like that.
Right.
Can you relate nu and T to this kind of.
Yeah. So basically, this will come a bit later. The idea is that the T and nu will be determined by your service requirements. So a service requires a certain nu, which is the quality or the fidelity of your tracking. So how well you have tracked. So more number of slots you have tracked, the better your tracking experience. Some applications such as parking assist does not need too many nu.
Yeah, but how do you fix it? Because you cannot. I mean, I expect that you relate it to some probability of detection, or I mean, some confidence on the probability of detection.
Yeah. So probability of tracking.
Yeah. Okay.
So probability of detection is in one slot.
Is in one slot. Yeah.
And we will see quite interestingly that the parameters which optimize the probability of detection might not be the ones which optimize the probability of tracking. Because of the simple reason that once you have access, you are guaranteed transmission in all the slots of that block. But for detection, you have slot wise, you can access or not access, or if you have slot allow, for example. Right. But the trade-off between T and nu, it's coming up. Yeah. So here it becomes a bit more really stochastic geometry metric, where it says, I want the meta distribution of the burst length, which means that I want the probability that the conditional CDF of the burst length is greater than beta. where the conditional CDF is the probability that the burst length was greater than nu for a given realization of the point process. So this will give me the fraction of radars in the network that experience a successful successive detection of at least nu slots in a sequence of t slots in at least beta fraction of the network realization. But this is something which was intractable. We couldn't characterize it, but we could calculate the first moment. The first moment tells us the average number of radars which will have a successful detection in at least nu slots in a sequence of t slots. So it's coming from this equation directly, but since PD is coming everywhere, so a little bit of algebraic manipulation is needed to convert it into in terms of the moments. So, but the moments help us get back here. Okay. So now we want to design this frame, which is quality of service aware frame design. Let's say I have a latency requirement by a specific use case. So low latency requirements such as lane change assistance, automatic energy braking may employ a TL or latency deadline of the order of 1 millisecond. It's not end-to-end latency, it's only over the radio, let's say. On the contrary, use cases with less stringent latency requirements such as parking assist, it can have several tens of milliseconds as the latency deadline. Furthermore, we introduce a yeah.
So this is better.
Sorry.
There is a constraint on latency, but you have to couple with the constraint on the reliability.
Yeah, that will be the nu. So we introduce the reliability measure based on nu. So a larger value of nu corresponds to a higher reliability requirement.
So earlier you were saying about the eco SNR. Right? So is that eco SNR also coupled in some way with reliability?
So the SINR is a metric of reliability in one slot, right? And then the subsequent SINRs together forms the metric of reliability on the. But the interference is of course already included in this formulation, right? So a larger value of nu, you need better reliability. Now I will say success for the tracking service to be rendered successful is that the use case necessitates that at least one successful tracking event, at least the ego radar experiences at least one burst of new consecutive successes within a deadline of TL. Now TL is not my block length. I will have to create blocks in it because if TL is my block length, then everybody has to access. Now I have to have this MAC protocol also. So if I create smaller blocks, right? So I will have more chances of access. So I will have more competition, more chances of competing to get the access. But if I get the access, large number of blocks create smaller block lengths, which reduces my chance of having new consecutive successes. So there is an optimal frame design that is needed. So let TL be divided into n access blocks, wherein each radar competes for access in each block. Each block is further divided into T slots like before, and each corresponds to one pulse width of the radar. Right. So now you have a train of pulse widths. The number of blocks is total latency deadline divided by length of the block multiplied by the pulse width. T must be necessarily larger than the requirement, otherwise you don't get nu more than T. Now the probability that you will get at least one access is, if delta is your MAC parameter or Aloha parameter, is 1 minus you never get access, which is 1 minus delta to the power n. N is the number of blocks. If you get access, PT is the tracking probability of successful tracking, probability that L is greater than nu. Now the trade-off is this: fewer blocks result in lower access chance of individual radars. So if you have TL divided into 2 blocks, you will have 2 possibilities of access. If you don't get access, you will fail anyway because you are not getting access within your latency deadline. But if you have fewer blocks, if you do get access, then each block, which is larger in length, enables you with a higher probability that the tracking length of the active radar exceeds the target nu. So here is our the simple problem. I want to maximize this probability. that I do get access, and if I do get access, I have a successful tracking, such that this constant on shortening or widening the block length. Right. The parameters lambda, the intensity of streets, the density of vehicles, etc., might not be known to the ego radar. This needs development of some data-driven algorithms. I mean, you would want to optimize the MAC parameter based on how many vehicles are there currently in the network, right? So if there are fewer vehicles, you can give all of them access, for example. Nevertheless, I mean, this we can find out by our previous data, how during the day the vehicle density changes, the MAC parameter which works in Paris may not be the one which works in New Delhi, so on and so forth. The case of delta equal to 1 corresponds to full interference. Everybody accesses always. In this case, regardless of the value of the tracking requirement, the optimal solution is to select only one block, because if everybody accesses, then you should have the possibility to give the entire block for them to attempt this successful tracking event. On the other hand, the case of nu equal to 1, which means you are not interested in tracking, but only detection, corresponds to this detection probability. Now, this optimal delta, of course, increases with lambda and lambda L due to an increase in interference. These are numerical results. I'll go to the details of the numerical results in a bit. But just before going to numerical optimization of the frame design, it's just that the n, which is the number of blocks, doesn't have a lot of flexibility of optimization, because first of all, it's an integer. And if you increase n from 1 to 2, which means you decrease the block length by 2 times. So each time you increase the number of possible accesses to each vehicle, you are really reducing the possibility of them having consecutive successes in a to the power sense. Right. Nevertheless, in real systems, you will have finite values of delta and finite values of n anyway. So you can just work around the parameters to find, for a given intensity of lines and intensity of vehicles, what would be the optimal parameter. So these are taken from this reference, which is from 3GPP Connected Roads of the Future, use cases, requirements, and so on and so forth. So we have adaptive cruise control, which has a latency requirement of 100 milliseconds, and go as low as lane change assistance, which I assume that would be even lower, but it seems that it's not very low. Park assist, very high requirement. Blind spot detection, very high requirement. The reliability is kind of back calculated in terms of how do you define success. So there, the success is generally loosely defined on whether you are calling some detection event as a success or not. But this column is manually curated a bit. So how do you define more reliability and so on? But this needs maybe more discussion in the specifications meetings. I don't know. We have delta star. We see that if you have, I mean, it depends on how, if you need low value of nu, you can have everybody try to access. Even if they fail sometimes, they just need some bunch of nu coming up together, right? Something like this. But more insights will come from these results. And this is a bit the main insight of this work. So there are some existing results on radar, automotive radar modeling using stochastic geometry, which also uses some MAC protocols to optimize the access in order to alleviate the impact of interference. The observation is that the aloha parameter which optimizes the detection might not be the aloha parameter which maximizes your tracking. And the reason is the same as I explained before. If you are only interested in detection, if you get an access, right, then you have to compete again for access, right? And then you are interested in, I mean, whether in the slot where I'm transmitting, whether I'm getting a successful detection or not. Whereas in tracking or block-based MAC, even if you get access, you are guaranteed chances of transmission in the entire block. So this might lead you to have larger values of aloha parameters for maximizing the tracking event. Tracking requirement, if you make it more stringent, then you have a possibility that you decrease if everybody accesses, right? So you have optimal delta for which you maximize the tracking event basically. The optimal delta changes, as I said, with lambda and lambda L. So for a given lambda L, if I increase the value of lambda L, my optimal access probability also decreases, which says that in cities with lot of dense streets behaves similarly to cities with fewer streets but more dense vehicles, right? So in both cases, you would have to optimize or lower the chances that each individual vehicle gets access to this probability. This, by the way, also can be tied to the communication system as well. So if you get access, maybe you would want to track and send something, or maybe receive and track as a result, and things like that. So this, ideally, it can be integrated with the side link of vehicle to vehicle, for example. You want to track and then if it's near, you want to send something. If it's far, you don't send something like this. So impact of QoS requirements. So for example, in lane change assist, I have a latency deadline of 10 milliseconds and a tracking requirement of 8 slots. So I have a lower amount of access probability because a lower amount of aloha probability, because even if I have access once, I just need access once. And when I have access, I just want others to not access, right? So if I keep delta very less, if I have sufficient number of blocks, I don't need access in all the blocks. I just need to access one of the blocks. And in that block, I want low interference because I want to achieve a very high or 8 value of this stuff. And the trade-off is both ways. If latency deadline is coming lower, you want to access more often because you are really pushing the ability of your access. And once you access, what is the interference that you are causing? It turns out that for most of our practical cases, n equal to 1, which is one single block with everyone accessing, gives the best performance. This is with real data. Right? But theoretically, it might be possible that you have better optimization. So in this case, if you have large beam width, you can have cases where your n equal to 1, which is one single large block in your latency deadline, can create an optimal access probability at around 0.4 or 0.5. But the amount of detection or tracking success that you get at that value is lower than you actually if you shrink the number of blocks to 2. The sizes of the blocks you shrink so that there are 2 blocks now, and you appropriately tune the aloha parameter such that in each of these blocks you have reduced interference. But now you just want access in only one of those blocks. It's fine if I get access in only one of those blocks and I am successful. Lower the value of nu, you can also have more number of blocks basically.
But on the order of magnitude, your y-axis real systems, I think, should be very close to 1.
Yes, yes.
So how do you interpret the values that you have here that are a bit disappointing? Let's say if you want to change lane and so on, you don't want 0.5.
Yeah. So there are 2 points why these values are like this. One is we have assumed that the oncoming traffic is like in front of you, and you are in the bore sight of the radar beam of the oncoming traffic. But generally, the lane is unless you are in India, the lane is a bit on the side, and you have a lower received power. Also, for dense street systems, we have ignored the penetration losses due to the buildings. So it will change, I think, drastically. Yeah. But even with, let's say, if these 2 assumptions are valid, even with real data for the detection case, we saw of the order of 0.3 and 0.4 for Paris, if you remember. So it's really not good in general. But of course, these are the modeling assumptions that we have of ignoring or over estimating the interference that I would receive. The key takeaways is that the BLP that we had introduced in the previous talk and rediscussed in this talk being a two-parameter model, can better emulate the inhomogeneity as compared to the Poisson line process. It was validated through real data. The Kolmogorov distance between the real data, the empirical CDF, and the CDF by best parameterized BLP was lower than the PLP. Of course, PLP has one parameter and less agility to adapt. The line processes and Cox processes driven by them can be used to model automotive radar networks. We saw how interference is critical to be modeled. This was experimentally proven. Then we modeled it and saw that the impact of interference can be taken into account on the basis of where you are, where your intersection is, and where the interfering vehicles are located. The key metrics of stochastic geometry, such as success probability, can be adapted to study radar networks, where we will call it detection probability. Fortunately, most of the modeling remains the same. So whoever has worked in stochastic geometry, you need exponential random variables for fading. Thankfully, the radar cross section is also exponentially distributed random variable, so all the equations follow in the same manner. Right.
It's an approximation, or
no, it's coming from a completely different field, but it's true. So there are 2-3 models. No, it's a feature of the target. So the target cross section area is exponentially distributed with some parameter. So the larger it is, the better you will be able to track it, detect it. The smaller it is, you will not be able to detect it. It behaves similar to the fading with parameter 1. Yeah. So this helps us carry forward all the equations from communication to detection. We proposed a new metric, which to the best of our knowledge has not been studied yet. It's called successful detection, and employed it to characterize the tracking probability of automotive radars. Works that we did to model the possibility of controllability of control systems. So in restless control systems, you need successive control inputs to be valid, because if you miss one control input, maybe you have to go back to the first state and then you regain your track of again observing the controllability. So we did the same modeling for that case as well. In a block Aloha channel access scheme, the Aloha parameter that optimizes the detection may not be the one that optimizes the tracking. And it depends on what values of tracking parameters you use and what is the latency deadline, so that you have that flexibility of designing it. So this brings to the last point, which is the tracking event can be designed based on the latency and QoS reliability QoS requirements of the application. And then that can be mapped back to the models of TL and nu and calculate the radar tracking probability and so on and so forth. So this brings me to the end of the presentation, and I'll take questions.
Your key metrics, I mean, your new metric, can you easily relate it to misdetection and
Yes. So I think once we characterize the SINR, the only thing that remains is where that boundary is put. So let me go to here. Yeah, this one. Right. So how many times? So this PDFs are because of the randomness of interference as well as the signal. The signal is because of fluctuating cross section, and interference is because of the fadings. Now across time instances, it's like independent PDFs that are coming up. So in how many successive such realizations, I'm having that well separated plots, right? More well separated, more will be your flexibility of improving the detection probability while maintaining the same false alarm rate. Right.
Here it is like this hypothesis classification.
Yeah, this is same as that, right? So given that you there's no signal, what is the probability that you detect a signal? Given that there is a signal, what is the probability that you detect a signal? That's detection, and so on.
I understand that is related, but can you derive the
We didn't try it yet. I think it apart from the SINR, so SINR removes the it removes the knowledge of where they are located. I mean, it tells you the relative separation, but it doesn't tell you the values here.
Yeah.
So maybe we need average signal power as well. Maybe one of the anchoring locations, and from there we study the separation. We didn't derive this yet. Yeah.
So I think the reader expect to have this classical parameter.
Yes, more than the reader, the reviewer. Yes. So we tried to do it for the detection. Right? It's difficult. So it's basically you are asking what is the CDF of interference. Right. So probability that signal plus noise plus interference is greater than a threshold. Let's say noise, if I remove, the misdetection is what is the probability that interference is greater than a threshold, which is the CDF of interference. Then you again need the Gil-Pelet's inversion theorem and things like that. Right. Okay, so if there are no other questions, thank you.
There are any questions? Maybe ask if there are questions.
I don't think so.
Yeah. Because I'm not sure they can hear me.
No, I don't think so.
No.
Okay. There is in the chat. No. Okay. Sorry. Okay. Thank you. Thank you.